Hi, boys and girls. This is your Thursday lesson. This is SLT 15. Please make sure you know that you're going to do two things today, and you're going to need your packet. So at some point during this video, please take out your packet and open up to page 108. We're going to do the concepts they're going to cover in this video are using similarity to solve problems in the real world, and then also we're going to talk about angle bisectors and the relationship within triangles. This last one is something that Miss Freed's class has already done, but I'll be pretty brief in describing this to my class. So basically, we use real similar triangles in the real world very often, depending on what your job is. But these kind of problems simulate where you might use the fact that you create similar triangles. So the first one would be, you know, things that you can't measure because they're too tall. You can actually create using certain tools. You can create straight lines that go from either your eye line or a particular machine that go directly up to the top of the tree. So when you do this and you do have something that you can measure within that eye line, so say you had a broomstick or you had a specific uh, figure that you could measure and realize that it was 2 meters, you can create two triangles this way where you know the distance from you or your machine to the, say, meter stick or whatever, and you could measure that, and you could also find the distance from you to the tree. What you can't measure is how tall the tree is. So using this information, you can set up a proportion. So that proportion is going to essentially be, um, excuse me, let me get a pen right here. So you can use this triangle. So you can say length of the smaller triangle, which is 3, and on top of that, you could say the height of this triangle, which is 2, is going to be in the same ratio because the big triangle and the small triangle are similar, as the length of the triangle, which would, instead of being 3, now it's 30, but you don't know the actual height of the tree, which we'll call x. So setting and solving this proportion would help you solve that problem. Another example of this is a lot of times we use shadows. Since the sun's rays are parallel, the triangles are going to be similar. So you have an unknown height and you have a known height, and you have a shadow of one and you have a shadow of another one, something else, that same known height. So what you could do is you could set a proportion between the unknown height, x, and say, the shadow was 4 meters, so we'll say 4. And then the known height we'll say was 12 over the shadow, which would be, we'll say 2. So knowing this information, you can set up a proportion. Same thing goes right here. Say you didn't know the Eiffel Tower's height, but you can find the length of the shadow, but you could measure a broomstick's height and the length of that shadow. So you can do this same proportion. Height of the tower to length of the shadow equals height of the known object over length of its shadow. And this will help us, since we'll know 3 of the 4 parts of this proportion, we'll be able to solve. So here's another example where you might not be able to measure all the way across let's say a river, but you could measure from M to K and make it, say it's 3 meters, miles, whatever. And you could measure from here to here, which is 4. And you would be able to measure down to here. We'll make that, say, 12. So the fact that you can use a carpenter's square to create a right angle here, what you're doing is you're creating a right triangle. And then by using that same angle, you can go down here and create an altitude. So here you have an altitude of a right triangle. So we can call this length K. This wouldn't make sense actually because the hypotenuse would have to be of the smaller triangle, the longest side. So we'll assume that this hypotenuse is 12, and we'll say that this is 8. Now, I don't know if I used correctly. I know I did not use correctly the 3 lines that will make a right triangle, but let's just assume that I did. So to find out what x is, which would be the length across the river, we would just have to use the knowledge that by creating a right triangle with an altitude, we have 2 similar triangles here. The big triangle is similar to this smaller triangle. So of the big triangle, I have the hypotenuse, which would be 3 plus x. And I also have the smaller leg of the big triangle, which would be 12. So I have hypotenuse over smaller leg of one of the triangles. So since I have another triangle that's similar to this small triangle, I can use those same numbers, well, not the same numbers, but the same thinking. The hypotenuse of the smaller triangle is 12, and the smaller leg of this small triangle is 3. And as long as you distribute the 3 to both of these and solve this equation, you can find out what x is, which is the distance across the river. You wouldn't have been able to do that unless you created similar triangles. So the first assignment you guys are going to have to do is on page 108 to 110. I'm going to explain in the video exactly where you can find the answers to those at the end of this video. So please make sure you keep listening until the very end of the video. The other concept that you had to learn today was that, well, yesterday we learned that if you have two similar triangles, anything that has to do with length is going to be in the same ratio. So if I happen to draw an altitude here and an altitude there, these would be in the same ratio as two of the sides. Or if I actually drew a median, which would cut this in half, and drew a median here, which would cut this in half, this side, the median, the length of the median would also be in the same ratio as one of the sides. But there's something that's true. That's if you have two similar triangles. In any one triangle, if you ever create an angle bisector, which would mean a line that cuts through and makes these two angles exactly the same. What's interesting, what happens in all triangles, is the way that it breaks up this side, and we'll call the length of this one A and this one B. The ratio of A to B will actually be the same ratio as these two sides. So if this was 12, for example, and this was 6, I know that A would be double what B was. If this was 6 and this was 18, I know that A would be triple of what B was. So if you ever have an angle bisector, the way in which it breaks up the other side will always be in the same ratio. So for example, if I knew that I had an angle bisector, and this was 5, and we didn't know the length of this, but we knew this was 10 and this was 4, I know that since this is an angle bisector, the way that 5 divided by x, that ratio, will be in proportion or be equivalent to 10 over 4. And there's other ways you could have said 10, the way that 10 and 5, that ratio, if I just go this side, will be in the same ratio as 4 to x. And that's true of any time you have a triangle with an angle bisector. The way it cuts these other two sides will be in the same ratio. So what you're going to do, there's two things you're going to do. You're going to complete page 13 to 17. These are numbers 13 to 17 from Mr. Katz's homework. That deals with the angle bisector. Now, everyone in Mr. Katz's and Miss Freed's class, you're going to complete pages 108 to 110 in your packet. And so you understand what that looks like. It's these pages. When you're done doing the problems, because we're going to quiz you on these concepts. When you're done, there's a video on wesleyanmath.org that is in Unit 2, Topic 1, that is titled Homework Problem Solutions for SLTs 14 and 15. When you're done, please watch this video to check your answers before you come to class. And that's today's lesson.